Okay, welcome back. Today's video is about the second component of okay, where is it? Second component of the leakage power or static power. For the first component, which was reverse bias PN junction current flowing through that's something we discussed in the last video. So the second component of the leakage power, the leaking power, mean that when we don't want it to consume power, but there's still some current is leaking, some power is consumed and dissipated in the form of heat. That is, this time is a channel, the actual channel leaking when it's not supposed to leak or not supposed to have current. So let's look into that. If you remember the very first video, I think when I started this series, very first video I said the whole digital IC or digital logic with 0 and 1. Let's say logic 0 is when it's off, logic 1 is when it's on. Okay, that whole thing works because we have a switch there. It's on and off. So when it's off, look, it's completely disconnected, no current. And when it's on, current flows. And then I said, okay, transistors, the CMOS transistor is closer to an ideal switch. We can, in this case, the CMOS transistor, gate, source, drain, NMOS. This channel is created here. When through gate voltage, we can control when this channel is created, and then through voltage here, we can push the current flow. And when we don't want this current, then we don't have enough voltage or less than VT voltage, if you remember, right? Then it's off. The ideal way is right, but when transistor length got shorter and shorter, and let's say it came in 0.35 micron or 0.25 micron and less, this channel relatively to this, this length, relatively to the depth of this source and drain, it became pretty equal or close. And that's where the short channel effects started happening. This lecture is, or this video is not about short channel effects. I'll hit those in a separate video when I talk about the scaling. But the key problem we started seeing was it's not off completely. Even when the gate to source voltage in NMOS case is less than VT, threshold voltage, there is still some current flowing. And this graph depicts that. So on horizontal, we have gate to source voltage. On vertical, we have this current flowing. And we know that this was the shape of this curve. But the interesting thing is around VT. So ideally, you were thinking that, okay, it will be like come here, or maybe it will come here and then go there, right? So there is no current here. But actually, there is a small amount of current. It decreases exponentially, but still there is a current even in this region. And what makes sense is when we were creating, remember, the VT is the gate to source voltage when is equal to VT in the channel. A strong inversion happens. But even before that strong inversion, there is some sort of inversion. And current can flow, a little drain voltage can pull it off. Or even when there is no drain voltage, there is enough current that, okay, it's not going to go quickly down. There, the current, the electrons start flowing. There is no abrupt. There is no like time at one time starts happening and another one nothing. No, it's a gradual process, and during that process, current is flowing. Now, even here in this curve, you see when gate to source of voltage, you're probably thinking, okay, yeah, it's fine, some current flows, but when I go to gate to source voltage 0, there's no current, so it's okay. What's the problem? Here is the problem. Let's look into this picture. This is I took it from this Intel Technology Journal in 1998. At that time, this was the technology. They had a little bit. So the curve is from 1 micron down to 0.8, 0.6, 0.35, 0.25, 0.1. Or you can also say this. 0.35 is 3, 50 nanometer. 2.25 is to 50 nanometer, 180 nanometer. And these days we are talking about 5 nanometer, 3 nanometer. So it's a while back. But the point I'm trying to make here, it is still valid. So they said, okay, as we scale down, transistor length gets smaller, it gets faster, so we can run at higher frequency. But at the same time, power is going up. And this gap is closing. They already then in 1998, we knew that was happening. So as the length, we are reducing the length so that we can get smaller transistor. And smaller transistor mean for the same area we can pack more transistor and add more functionality. And as that happens, power is because there are more transistors, we are increasing the frequency and all that. So net effect is power going up. So as a result, what we do is we cannot keep the VDD at the same value as in the previous generation. Let's say we were here 0.25, whatever voltage of 0.35, we need to bring it down. Not as much, because keep in mind there are already boards and everything set up customer's hand with a certain voltage. So it's not a simple thing, hey, we're just decreasing the voltage. They have to change everything. Okay. But still, to reduce this power, we wanted to reduce this VDD. Because okay, with a less VDD we can make some compromise and still get a performance, but not as much because we need to control power. You understand that? So length gets smaller. We like to make VD smaller. And what happens? Can we keep VT at the same point? You're probably thinking, okay, it's before the swing was, right? The input voltage will swing from 0 to 1. 1 means the VDD. Similarly, output voltage will change as well. 0 to 1 means 0 to VDD. So let's say if VDD was here. Now we are reducing VDD here. Now threshold voltage, if it's fixed, so you probably be thinking it's fine, keep this guy fixed at the same, this place. Here. So this is the delta between this and this is the delta. You probably be thinking, okay, that's fine, you reduce it, your dynamic power is going down because remember CL VDD square, VDD is reduced, there is a huge impact on power. So we can reduce power and just keep the threshold the same. Now with the threshold keeping the same, there is definitely, I'm not going into that, or should I go into that? So think of that, VT is the point where transistor turns on. You need a decent swing. So here where the swing will be very small, right? So it's off and on. So it's a very short time. But the point I want to make is a little bit different one. Assume that, remember the current is proportional to, if you remember, this was our equation. That's I intentionally mentioned that, okay. And here is VGS minus VT. The gap is very small here if I stay here. The gap, remember, so that means even though we have decreased the length, which is good for current, right? But current will increase. But VGS minus VT is actually the thing that derives the amount of current. But that will be very small if we don't change VT. So the noise margin logic levels are impacted, but I'm only talking about the current faster, the circuit is faster or slower. If I keep the same VT but reduce the supply voltage, this gap, which is VGS minus VT, is actually decreasing. When this decreases, it decreases the current. So transistor will be slower. So we got down, we made a smaller transistor hoping that would be faster, but it's actually turned out that it's not faster. So In order to hit that, we need to reduce voltage, threshold voltage, so that now the gap is kind of the same here. Remember in that era, Intel was every time you increase the frequency, higher frequency PCs, higher frequency PCs. So this was important to do that, to bring a better frequency and better performance, faster and faster PCs, CPUs. Um, so we had to make that delta. But problem is when you bring VT here, if you bring VT here, then look at this thing. Now this curve is going to be the same. It's just shifted. Now the problem is when VGS is 0, it's not 0 current, there is some current. Now think about millions and millions of transistors. Even when they're not switching, even when they're not doing anything, they're still leaking. So power is generated. Your chip is getting hotter and hotter. So you see the problem with the leakage current or leakage power. Here this thing is show the same thing. These are different threshold voltage and the off current, and you can see that when you drop the threshold voltage to this 150 millivolt as opposed to let's say 500 millivolt, the amount of off current is much higher. So that's the problem. By the way, I forgot to mention, this is that gap between VGS and VT I was mentioning. But anyway, I hope you understood and this concept. So that's the problem with lowering the VT. It helps performance. Performance is good, but the power is not good. The typical things that in physical design people do that a lot, and have been doing that for several generations of process scaling, is that we use a mix of different cells with different threshold voltages. So typically we have a higher threshold or higher VT and lower VT cells like AND gate, NAND gate, and not all the standard cell in the library. They are available. There is a high VT standard cell library. There's a lower VT standard cell library. So somebody can ask you, okay, what's the difference between the two? So higher VT, and now based on this description, hope you understand that. A higher VT means lower leakage, right? I of low, yeah, you understand that, low leakage. But the problem is this VGS minus VT, this gap between VGS minus, it gets smaller. And when this gets smaller here, what happens? Current is less, transistor is slow. So higher VT means slower transistor, but good for leakage, lower leakage. The same, the opposite. Lower VT, here, higher leakage. But the good thing is this gap is bigger. Overdrive, this is called overdrive. Like how much more VGS compared to VT, that's really pushing for more current. So current is higher, transistor is faster. So what we do is, in our design, not every timing path is equally critical. There are 5 or 10% of the path which is super critical. They are driving and they are setting the frequency of the design, and those are the ones where we need to use faster cells. So the point is, okay, there you can use a lower VT cells. They will leak more power, but it's a small percentage of your design, and that's where you need a frequency, high frequency. So you use the lower VT cells for those parts. But for the rest of the design, 90% of the design or 80% of the design, you use cells with a very low leakage. Okay, so higher VT. Then you need to be careful with some of the noise margin because your logic levels are disturbed, but at least for the power, those are good. So that's it. That's all I wanted to tell you about leakage power. Hope you understood that. And I think that concludes my series on power. I have a couple of topics left on CMOS, so most likely I'm going to hit scaling in the next CMOS videos. And after that we will look into AND, OR, NOR, NAND, flip-flop, some of the CMOS build-up of those. and we will look into setup hold times for the flip flop. So I think within a week I will wrap up CMOS and then we can start on physical design. Hope this video was useful. Thank you so much. Talk to you next time.